Hello, this is the first video in the Critical Path Analysis series for OCR Discrete Further Maths. We'll be looking at how to construct an activity network from a precedence table. Let's look at an introductory example of what critical path analysis is all about. Say that every morning you want to toast 3 pieces of bread under the grill, and the grill will take 2 pieces of bread at a time and will take 30 seconds to toast one side of the bread. How long will it take to toast all 3 pieces of bread? Amy says it will take 2 minutes. Bethan says it will take 1.5 minutes. So who is correct? Well, Amy's reasoning works along the fact that both slices A and B will have side 1 done, and then side 2, and then slice C, side 1 and then 2, each taking 30 seconds. So in other words, 4 times 30 gives for 2 minutes. Bethan has probably decided that she will do slices A and B on side 1 and then swap one of those slices for C. So C will be side 1 and say A side 2 at the same time, and then C side 2 and B side 2 at the same time, thus only needing 3 lots of 30 seconds for 1.5 minutes. So this is a relatively trivial example of how prior planning and use of resources can result in greater efficiency. So critical path analysis, known as CPA, enables us to plan and monitor complex projects so that they are approached and carried out as efficiently as possible. Generally, the question is, given the conditions, what is the shortest possible time the project can be completed in? We will assume that tasks can be carried out simultaneously whenever conditions allow it. In general, a project is modelled using precedence tables and activity networks. First, we need to list the activities within the project and their durations, in terms of the time required. Once we've decided the logical sequence of activities and also have identified which activities depend on other activities having been completed before they can be started, then we can put together those precedence tables and start to build an activity network. Let's look at an example of the stages involved in recording and promoting a compact disc. So here we have the processes which we've identified as A through to J, and the duration of time in whatever units that we think it will take. So the preceding activities column only shows the immediate predecessors. For example then, let's look at activity D, tape to CD. Well, you've got to have taped the performance, i.e. activity A, and finished that activity before we can start activity D by putting the tape to the CD. If we look at activity E, to produce the cover, then you've also got to have completed the activity design the cover before you can go on to produce it, and so on. If we look at J, adverts in the press, that relies on having booked those, having dispatched the CDs to the shops, and having had it played in the radio first. Of course, this is again not a particularly complicated example. CPA in general is used for complex projects in industrial production, maintenance or construction, or even by individuals who are, for example, building or renovating their own home, when you would need to think about things like the first fix and second fix, electrics and plumbing, in order of precedence compared to plastering. This is the vocabulary you need to be aware of. So CPA is the process of analysing a project to enable the best use to be made of time and other resources. We've already seen an example of a precedence table. We will go on to look at examples of precedence networks or activity networks. The idea of a source node is that it is the first part of the activity network, so if you like, time 0. And the sync node is where we are finishing the project. An event occurs when an activity can start, or when the whole project is complete, and these are represented by the nodes or vertices of a network. An activity is a job or process or task that forms part of an overall project, and these are represented by the arcs or edges in the network. Merge nodes represent events into which a number of activities enter and one or several leave. Burst nodes represent events that have one or more entering activities generating a number of emerging activities. Nodes may represent both merge and burst events at the same time. A dummy activity is one with no time or cost, whose purpose is either to show dependencies or to satisfy the condition that there can be at most one activity between any two events. We'll look at dummy activities in more detail later on. So let's construct an activity on our network for a process. This is done step by step, working from left to right. Let's start with a simple example. So you can see that we would start by the node, the source node, we'll label it 1, and that A and B have no preceding activities, and therefore the arcs representing A and B can both start at time 0. And we'll put an arrow on to show that those activities are progressing. Right. If we have that 2 is the node or the event that says for A, activity A is completed, and we can label the node 3 as the event which says that B is completed. And you'll note that in this simple example, no weights are given, or no durations. Generally speaking, if I was drawing this on a bit of paper, I'd do it in pencil, as we may need to alter it as we go along. So you can see that the activity C depends on A being completed, but from A, the node A is completed. Activity D requires B to be completed, so therefore it will start from node 3. You can see that F depends on both C and B being completed, and I can use one node to represent C and D being completed, from which F can then start. G depends on E and F. And E depends on B as well. So E would start with B being completed, and I can have E and F finishing together, or being completed together. And then G, activity starting, and then the sync node will show that the whole task or project is completed. Looking at a second example, again we would draw a start node to begin with. We would look at the fact that in this case A, B and C activities do not have any preceding activities, so they can all be added from time 0, or the start node, or source node. And then we will decide how we go from there depending on the precedences. We can see that D depends on activity A, and therefore we need a node to show that A is complete, and D would then start from there. Similarly, we need E to have had B completed before it can start, and therefore we would do a node to show B is completed and then add in the arc E. These are drawn as if they're converging because later on you can see that F and G need both D and E to be completed. So we can have one event or one single node showing D and E are completed, from which F and G can then emerge. Looking then at H, that depends on F being completed, so that would go there. And then I needs to follow G. And then I can see that activity J needs C, H and I. So they will all finish at one node. You can see if I extended that arc C, remembering that the network there's no relevance in terms of the duration isn't shown by the length of the arc, we're just showing the relationships. Once we've done J, we can finish at node 8. And you can see from the fact that we had to extend that arc C and converge D and E and then F and G emerging and so on, why I recommended that you would start to draw these in pencil until you're sure how it's going to work out. Remember that the arcs represent activities and that these must be uniquely identified by start and finish nodes. So, and this slide shows that each activity is identified by a uniquely ordered pair of nodes, ij. So if we look at activity A, we can see that it is identified by starting at node 1 and finishing at 2. Activity B starts at 1, finishes at 3. C starts at 1, finishes at 7. D starts at 2, finishes at 4, and so on. Right, so you cannot have activities starting at the same node but also then finish at the same node. And we'll go on to look at this in more detail when we consider dummy activities in due course. The next video, 1.2, will cover this idea of using dummies in activity networks.